Mercury, the smallest planet in the solar system, and it is also the planet closest to the Sun, making it the most difficult of the planets to see with the unaided eye. Because its rising or setting is always within about 2 hours of the Sun's, Mercury is never observable when the sky is fully dark. Mercury's average orbital distance from the Sun is 58 million kilometers, 36 million miles, and it has the shortest year, a revolution period of 88 days. In comparison, the mean distance of Earth from the Sun is about 150 million kilometers, 93 million miles. Mercury is the smallest planet in the solar system and the closest to the Sun, which it circles at great speed. This proximity means temperatures on the surface are extremely hot and makes it hard to explore. Mercury is the smallest planet in our solar system and nearest to the Sun. It's only slightly larger than Earth's moon. From the surface of Mercury, the Sun would appear more than 3 times as large as it does when viewed from Earth, and the sunlight would be as much as 7 times brighter. Mercury, planet, is the closest planet to the Sun and one of the most scientifically intriguing worlds in the entire solar system. Although it is the smallest of the 8 major planets, its importance in planetary science is immense because it preserves clues about the earliest stages of solar system formation and the physical processes that shape rocky planets under extreme conditions. Its proximity to the Sun exposes it to intense radiation, gravitational influence, and solar wind interactions that make it fundamentally different from most other planetary bodies. At first glance, Mercury may appear simple and barren, but modern exploration has revealed a far more complex world with a deep internal structure, a dynamic interaction with space, and a geological history that continues to challenge scientific understanding. From Earth, Mercury has always been a difficult planet to observe. It never strays far from the Sun in the sky, meaning it is only visible briefly during twilight hours. This limitation meant that ancient civilizations saw it as a fleeting point of light, moving quickly across the sky compared to the background stars. The Romans named it after their swift messenger god Mercury because of this rapid motion. For centuries, observations were limited and fragmented, leaving many aspects of the planet's true nature unknown. Even after the invention of telescopes, Mercury remained difficult to study due to atmospheric distortion and its proximity to the Sun's glare. As scientific tools improved, Mercury gradually transformed from a mysterious wandering light into a physical world with measurable properties. Astronomers determined that it was a rocky terrestrial planet, similar in some respects to Earth, Mars, and Venus. However, it quickly became clear that Mercury was unusual. Its orbit is highly elliptical, and it moves faster than any other planet in the solar system, completing a revolution around the Sun in just 88 Earth days. Yet its rotation is slow, taking about 59 Earth days to spin once on its axis. This creates a unique relationship between its day and year, where a single solar day lasts far longer than its orbital period. This strange rhythm contributes to extreme variations in temperature and illumination across its surface. The internal structure of Mercury is one of its most remarkable features. Unlike Earth or Venus, Mercury has an extremely large metallic core that dominates its interior. This core, primarily composed of iron, makes up a much larger fraction of the planet's volume than expected for a rocky world of its size. Surrounding this core is a relatively thin silicate mantle and crust. This unusual composition gives Mercury an exceptionally high density, second only to Earth among planets in the solar system. Scientists have long debated how this structure came to be, and several theories attempt to explain it. One possibility is that Mercury originally formed as a much larger planet but lost much of its outer layers due to a massive impact early in its history. A collision with a large planetary body could have stripped away much of its rocky mantle, leaving behind a dense iron-rich core. Another hypothesis suggests that intense heat from the young Sun may have vaporized part of Mercury's outer material before it fully formed. In this scenario, solar radiation would have played a major role in shaping the planet's final composition. Both theories point to a violent early solar system where planetary bodies were frequently reshaped by collisions and extreme environmental conditions. Mercury's surface reflects this violent history. It is heavily cratered, resembling Earth's moon in appearance. These craters were formed over billions of years as asteroids and comets collided with the planet. Because Mercury has no substantial atmosphere to slow down or burn up incoming objects, impacts strike the surface directly, leaving permanent marks. This lack of atmospheric protection also means that there is no weathering or erosion to erase these features, allowing Mercury's surface to act as a preserved record of early solar system bombardment. Among the most striking surface features are enormous impact basins, formed by collisions so powerful that they affected the entire planet. One of the largest is the Caloris Basin, a massive crater spanning more than 1,000 kilometers. The impact that created it was so energetic that it likely triggered seismic waves that traveled around the planet and may have influenced volcanic activity on the opposite side. Surrounding this basin are chaotic terrains and fractured regions that show how the crust responded to extreme stress. Mercury's surface is also marked by long cliff-like structures known as lobate scarps. These features were formed as the planet cooled and its interior contracted. As the metallic core slowly lost heat over time, the entire planet shrank slightly, causing the crust to buckle and fold. These scarps provide direct evidence that Mercury is still undergoing slow geological change, even though it lacks active plate tectonics like Earth. This gradual contraction is one of the clearest signs that Mercury's interior is still evolving. Despite its appearance as a dead and airless world, Mercury does exhibit subtle geological activity. There is evidence that volcanic processes once shaped parts of its surface. Smooth plains found in several regions suggest that lava once flowed across the planet, filling older craters and creating relatively flat terrain. These volcanic deposits indicate that Mercury once had enough internal heat to support widespread volcanic activity. Over time, as the planet cooled, this activity diminished, leaving behind a mostly static surface. Mercury's environment is dominated by extremes. Without a meaningful atmosphere, there is nothing to regulate temperature or shield the surface from solar radiation. As a result, temperatures vary dramatically between day and night. On the sunlit side, temperatures can become hot enough to melt certain metals, while on the night side they can drop to levels colder than many regions of the outer solar system. This extreme temperature range is one of the most dramatic in the entire solar system and highlights the importance of atmospheric insulation in regulating planetary climates. Instead of a true atmosphere, Mercury possesses a very thin exosphere made up of atoms that are constantly being released from its surface. These atoms are knocked loose by solar wind particles, micrometeorite impacts, and radiation. Because there is no significant atmospheric pressure, these particles do not collide frequently and instead drift through space before escaping or being reabsorbed. This creates a constantly changing and extremely tenuous envelope around the planet. Solar wind plays a particularly important role in shaping Mercury's environment. As the closest planet to the Sun, it is continuously bombarded by high-energy particles and radiation. This interaction not only affects the exosphere but also gradually alters the surface itself through a process known as space weathering. Over time, solar radiation changes the chemical and physical properties of surface materials, darkening and modifying them. This makes Mercury an active participant in a constant exchange of material with its surrounding space environment. Another fascinating feature of Mercury is its magnetic field. Despite its small size and slow rotation, the planet generates a global magnetic field similar in structure to Earth's, although much weaker. This field is believed to be generated by the movement of molten iron within its outer core. The existence of such a field suggests that Mercury's interior remains partially liquid, which is surprising given its long history of cooling. Understanding how this magnetic field persists has become one of the central questions in Mercury research. Mercury's rotational dynamics also add to its uniqueness. It is locked in a spin-orbit resonance where it rotates 3 times on its axis for every 2 orbits around the Sun. This unusual relationship affects how sunlight is distributed across its surface and contributes to complex patterns of heating and cooling. Some regions experience prolonged periods of sunlight, while others remain in darkness for extended periods. This resonance is the result of long-term gravitational interactions with the Sun and represents a stable but unusual orbital configuration. As space exploration advanced, Mercury became the target of dedicated spacecraft missions that revolutionized our understanding of the planet. The first spacecraft to visit was NASA's Mariner 10, which flew past Mercury in the 1970s and captured images of about half its surface. Despite its limited coverage, it revealed a heavily cratered landscape and confirmed the presence of a magnetic field. However, much of the planet remained unexplored for decades afterward. A major breakthrough came with the Messenger mission, which became the first spacecraft to orbit Mercury. It provided detailed maps of nearly the entire surface and uncovered a wealth of new information. Messenger confirmed the presence of water ice in permanently shadowed craters near the poles, discovered variations in surface composition, and provided insights into the planet's geological and magnetic history. These findings dramatically changed the perception of Mercury from a simple, inactive body to a complex and evolving planet. The discovery of water ice was particularly surprising given Mercury's proximity to the Sun. However, the planet's nearly zero axial tilt creates permanently shadowed regions in polar craters where sunlight never reaches. In these cold traps, temperatures remain low enough for water ice to persist over long periods. This ice is believed to have been delivered by comets or asteroid impacts and preserved in these shadowed regions. Its presence has important implications for understanding how water is distributed across the solar system. Messenger also revealed that Mercury's exosphere is more dynamic than previously thought. It contains elements such as sodium, potassium, and oxygen, which are constantly replenished by surface interactions. This discovery showed that Mercury is not chemically static but instead actively exchanges material between its surface and surrounding space. Following Messenger, international collaboration has taken Mercury exploration further with the Bepi-Colombo mission, jointly developed by European and Japanese space agencies. This mission is expected to provide even more detailed insights into Mercury's magnetic field, internal structure, and surface composition. Its complex trajectory, involving multiple flybys of Earth, Venus, and Mercury, highlights the engineering challenges involved in reaching such a sun-close world. Mercury's exploration is not only about understanding a single planet but also about gaining insight into planetary formation and evolution more broadly. Its extreme environment makes it an ideal laboratory for studying how planets respond to intense solar radiation and gravitational forces. It also provides a comparison point for exoplanets that orbit very close to their stars, many of which may share similar characteristics. The study of Mercury's interior suggests that its large iron core may still contain enough heat to sustain convection, allowing its magnetic field to persist. Some theories propose that lighter elements mixed within the core help maintain this activity. Others suggest that early tidal heating may have contributed additional energy during the planet's formative years. These questions remain active areas of research and are central to understanding planetary magnetism. Mercury also plays an important role in comparative planetology. By studying it alongside Earth, Venus, and Mars, scientists can better understand how different initial conditions lead to divergent planetary outcomes. Mercury represents one extreme end of the spectrum, showing what happens when a planet forms close to a star and undergoes intense thermal and radiative stress. Despite decades of study, Mercury still holds many unanswered questions. Its formation, internal structure, magnetic field, and long-term evolution remain active areas of investigation. Each new mission and observation adds another layer of understanding while often revealing new mysteries. In conclusion, Mercury is a world of extremes, contradictions, and hidden complexity. It is a small planet with a massive core, a scorched surface with hidden ice, and a weak atmosphere with a dynamic interaction with the solar wind. It is both ancient and still evolving, both simple in appearance and deeply complex in structure. Its study continues to reshape our understanding of planetary science, offering insights into the formation of rocky worlds and the forces that shape them over billions of years. As exploration continues, Mercury will remain one of the most important keys to understanding not only our solar system but also the countless planetary systems beyond it. Thank you for watching this video.